Hi, this is Alex from devstories.eu. Biopython Fundamentals, Episode 18 of 18. You just ran an RNA-seq experiment, and now you are staring at an expression matrix with 10,000 rows. Finding meaning in that raw data is impossible until you group those genes into a handful of distinct biological responses. That is exactly what cluster analysis for gene expression does, using the Bio.Cluster module. When you analyze microarray or RNA-seq data, you are tracking the activity of genes across different conditions. Take a concrete scenario. You have expression data for 1,000 genes measured across 4 heat shock time points. You want to identify which genes behave similarly. Perhaps 50 of them spike at hour 2 and drop at hour 4. Genes with matching up and down regulation patterns often share biological pathways or regulatory mechanisms. Finding these cohorts manually across thousands of rows is a non-starter. The Bio.Cluster module contains a C-based core designed specifically to process this type of matrix data efficiently. Your first step is getting the data into Biopython. Instead of writing custom parsing logic, you pass your tab-separated text file to the module's read function. This returns a specialized record object. This object holds your numerical expression matrix, but it also keeps track of your gene identifiers and the names of your experimental conditions. With the data loaded, you apply a clustering algorithm. The most common approach is k-means, executed using the k-cluster function. K-means partitions your items into a predetermined number of groups, represented by the variable k. You pass the data matrix and your chosen k value into the k-cluster function. The function then returns an array assigning every single gene to a specific cluster ID, along with an error value that measures how tightly packed those clusters are. Because the algorithm starts with random assignments, you typically run it multiple times and keep the iteration that yields the lowest error. Here is the key insight. The algorithm groups genes based on a distance metric, and you must choose that metric carefully. If you use standard Euclidean distance, the algorithm groups genes that have similar absolute expression levels. But if you want to group genes by the shape of their expression curve over time, regardless of their starting baseline, you must instruct the k-cluster function to use a correlation-based distance metric instead. K-means requires you to guess the number of clusters up front. If you do not know how many distinct responses exist in your heat shock data, you can use hierarchical clustering instead, via the tree cluster. Rather than forcing genes into flat buckets, tree cluster builds a hierarchy. It finds the 2 genes with the most identical expression patterns and links them. It then finds the next closest gene or pair and links those, building a branching tree structure called a dendrogram. Once the tree connects all 1,000 genes, you can observe the overall structure of the data and slice the branches at whatever level makes biological sense. Since this is the final episode of our Biopython Fundamentals series, I highly recommend opening the official Biopython documentation and trying these clustering functions on a real dataset. You can also visit devstories.eu to suggest topics you want covered in future series. The ultimate goal of running these algorithms is not just sorting numbers into buckets, but uncovering the shared biological logic that forces those genes to activate together. That's all for this one. Thanks for listening, and keep building.